Welcome back to Saltwater Stories.
Oh, we are so excited you're joining us again.
It's great to be here.
Today we're journeying deep, deep down into the ocean's, well, hidden machinery, you could say.
Mm.
We're uncovering this incredible invisible secret. And no, it's not a giant sea monster or a long-lost pirate ship.
Although those are cool too.
Definitely. But this is different. It's a force, a huge, powerful force that acts like a hidden switch.
Yeah, flicking that switch can turn these massive, almost empty parts of the ocean into like biological hotspots almost overnight.
A supermarket of the sea.
Exactly. It's the engine that drives some of the biggest fisheries on Earth. It's why millions, literally millions of seabirds flock to certain spots.
And it's key for the survival of the absolute biggest animals ever to exist on our planet.
Yet, most people have never even heard its name.
So what is this amazing secret?
We are talking about the secret pump of the sea, ocean upwelling. Okay, now before we dive into the how of it all, the science, let's go on a little adventure first, just to understand why it's so important.
Good idea. And for that, we need to meet someone. A tiny, tiny traveler, but a very, very old one.
Ooh, intriguing. Who is it?
Okay, imagine. Imagine you are a microscopic droplet of water. And let's call you Drip.
I Drip.
Now, Drip is having a pretty long and honestly a pretty boring life. For the last, say, 500 years, Drip has just been sitting there, still, quiet, in the pitch black, silent, deep ocean, maybe 2 miles down.
500 years. That's before smartphones, before cars.
Way before. Think Knights and Castles kind of time, and Drip's just been waiting in the freezing cold darkness.
And Drip isn't just plain water, right? You said it's carrying something.
Exactly. Drip is cold, super heavy from all the water pressing down, and it's loaded with treasure. Over those centuries, tiny bits of dead stuff have rained down from the sunny surface waters.
Scientists call that marine snow, right? Like a constant snowfall of tiny particles.
That's the stuff. Bits of dead plankton, fish scales, poop, all sorts of things. And down in the deep, bacteria break it all down, decompose it.
Okay.
And that process releases all the essential goodies back into the water, right next to Drip. So Drip is now full of these like ghostly leftovers, perfectly dissolved ancient nutrients, ocean vitamins.
So Drip is basically a tiny 500-year-old bottle of super concentrated fertilizer.
You got it. Then suddenly, after all that waiting, the waiting is over.
What happened?
Drip feels this pull. It's not violent, not an explosion. It's like joining this incredibly slow, but immensely powerful, great ocean elevator.
Upwards.
The great ocean elevator, I like that.
Yeah. The crushing pressure starts to ease off little by little, and Drip begins this enormous journey up, up, up from the darkness, heading towards the light it's never known.
Wow. So rising up through miles of water.
Up, up, up it goes. And finally, after what must feel like ages, Drip bursts out into the warmth, the blinding sunlight of the surface, the photic zone, that top layer where sunlight reaches.
Freedom and sunshine. And Drip has delivered its precious cargo, that cold water, packed with all those ancient nutrients right where it's needed most.
And does anything happen right away?
Instantly. The moment Drip arrives, that nutrient treasure it carried all this way, it gets slurped up by a tiny microscopic green cell, a phytoplankton, a tiny ocean plant.
Like, immediately.
Just like that. Drip's nitrogen, its phosphorus, all that good stuff helps that tiny plant grow big and strong using the sunlight for energy.
Okay, so Drip fueled one tiny plant. That's cool, but...
But that's just the start. The food chain kicks into high gear like really fast.
How fast?
Well, that single phytoplankton cell Drip fed, it gets eaten by a slightly bigger creature, maybe a tiny shrimp-like animal called a krill.
Okay.
But that krill isn't alone. It's part of a massive swarm, billions of them, all suddenly feasting on this explosion of phytoplankton growth.
An all-you-can-eat buffet.
Totally. And then, faster still, that krill gets gulped down by a little fish, maybe a shiny sardine, and that sardine is part of a huge, shimmering school stretching for miles, maybe.
Wow, okay, this is speeding up.
And then, whoosh, that sardine leaps, maybe trying to escape something, and gets snapped right out of the air by a big seabird, like a gannet or a pelican, soaring overhead.
No way.
Way! And just like that, Drip's mission is complete. In maybe just a few weeks, the nutrients Drip guarded for 500 years in the dark abyss traveled all the way up into a bird flying in the sky. It connected the deepest ocean to the world way above.
That's actually incredible. From the bottom of the ocean to the sky in weeks.
Powered by upwelling.
Okay, so that's why it matters. Our mission today, then, is to figure out the science behind Drip's amazing elevator ride. What invisible power is moving all that water, and what happens when this elevator really gets going?
Let's get into it. The secret science of ocean upwelling. So let's break it down. Upwelling. The name kind of gives it away, right? Water welling up.
Upwelling. Makes sense. But you said it's special water.
It is. It's specifically the vertical movement, the up and down movement of deep, really cold water that's packed with those nutrients we talked about.
Okay, cold and full of goodies.
And it rises up to the surface.
Yep, it rises up to replace the warmer, lighter surface water. That surface water is usually nutrient poor because the plants up there have used everything up. And importantly, that surface water has been pushed away somehow.
Pushed away. Hold on. I thought ocean water mostly moves sideways, in big currents like the Gulf Stream.
Yeah.
Why does it suddenly shoot upwards?
That's the key insight. The upwelling itself, the vertical part, is actually a reaction. It happens because something else is happening horizontally,
Yeah.
pushing that surface water away.
A reaction. Okay, explain that.
Think about maybe a swimming pool. If you stand at one end and use a big board to push the water away from you towards the other end,
Yeah.
the water level right in front of you drops for a split second. But the pool has to stay level, right? So water from deeper down or from the sides has to immediately flow in to fill that space.
Gotcha. So pushing water away horizontally creates a sort of temporary hole at the surface. Exactly. And in the vast ocean, when you push surface water away from a large area, the quickest way for the ocean to fill that gap and keep its level is to draw water straight up from below, from the deep.
So something pushes the top layer aside, and the deep water rises to take its place. That makes sense.
That's the core mechanism.
Okay, this feels like a good time for one of our analogies to help everyone picture this. How about the giant smoothie?
Perfect analogy. Okay, imagine you made this amazing, super healthy smoothie packed with fruit, maybe some spinach, seeds, all the good stuff.
Yeah.
But you let it sit on the counter for a while. What happens?
Oh, all the heavy, yummy bits sink to the bottom, and you get that watery layer on top.
Exactly. The heavy, nutrient-rich fruit and stuff, that's our deep, cold, nutrient-packed water. It's settled down low. The thin, watery juice on top, that's the warm surface water. It's used up its goodness. It's nutrient-poor.
And if you just sip from the top with a straw, it's pretty bland.
Right. No flavor, no energy. Now, upwelling is like using a giant straw, but instead of sucking up, imagine you blow air across the top of the smoothie.
Glow across the top.
Yeah, that pushes the watery top layer away to the sides of the glass. And what happens the moment that top layer is gone?
The thick, fruity stuff from the bottom would swirl up to fill the space.
Precisely. Suddenly, the whole top of your smoothie is rich, thick, and delicious again, ready to fuel whatever eats it. That deep water rising up is that burst of flavor. It's the ocean's natural fertilizer delivery system.
Okay, the smoothie helps with the nutrient idea. What about the temperature and why the water moves? Let's try the reverse lava lamp.
Good one. Okay, everyone knows a lava lamp, right? You've got that gooey wax stuff at the bottom.
Yeah, and the light bulb heats it up.
Right. The heat makes the wax less dense, lighter, so those blobs detach and float upwards through the liquid.
Mesmerizing.
It is. Now, upwelling is kind of the reverse density-wise. The surface water is already warm from the sun. It's light, less dense, like the liquid in the lava lamp.
Okay, and the deep water.
The deep water is really cold.
Yeah.
And cold water is denser, heavier, like the wax before it gets heated.
So in upwelling, we're not heating the deep water to make it rise.
No, not at all. Instead, something, usually the wind, as we'll see, pushes that light, warm surface water out of the way.
Like clearing the path.
Exactly. And because that deep water is naturally denser and heavier, it doesn't need encouragement to sink, usually. But here, the lighter water above it is removed. So the dense, cold water is basically forced upwards to fill the space left behind. It's like it's actively replacing the lighter water that got blown away.
So push the light stuff away, and the heavy stuff takes its place. It's almost like gravity working in reverse because of the hole created at the surface.
That's a great way to think about it. The system wants to find balance, and the dense water rising is how it does it when the light surface water is removed.
All right, this is fascinating. We know what upwelling is cold. Nutrient-rich water rising. And we know why it rises because the surface water gets pushed away. Now, the really cool part. How does that surface water get pushed away so effectively? This involves some amazing planetary science.
It really does. It's not just a random breeze. You need 3 key ingredients working together perfectly. Driver number 1 is pretty straightforward. Wind power.
Just wind.
Not just any wind. You need a strong, steady wind blowing over the ocean surface for a good amount of time, days, weeks even. And critically, it often blows in a consistent direction, usually parallel to a coastline.
Parallel, like blowing alongside the beach, not directly towards it or away from it.
Exactly. That constant blowing creates friction, a drag on the water surface. We call it wind stress. That's the initial energy that gets the whole elevator moving.
Okay, strong, steady wind along the coast. But wait, if the wind is blowing, say, south along the California coast,
Yeah.
why doesn't the water just get pushed south too? Why does it move offshore away from the coast to create that gap? That seems weird.
Ah, that is the million-dollar question. And the answer lies in driver number 2, the Earth's magic spin. The planet is spinning.
Of course. Around and around every day.
And that constant rotation has a really strange effect on things that move over long distances across its surface, like wind and, crucially for us, large patches of ocean water. It makes them appear to curve. This is called the Coriolis effect.
The Coriolis effect. I've heard of that. It affects hurricanes and stuff, right?
Yeah.
How does it work?
Let's try an analogy. Forget the complicated train one. Imagine you're standing right at the center of a huge, fast-spinning merry-go-round.
Okay, getting dizzy already.
And your friend is standing on the outer edge, directly across from you. If the merry-go-round is stopped, you could toss a ball straight to your friend, easy peasy.
Yep, catch.
But now the merry-go-round is spinning really fast. You throw the ball straight towards where your friend was. But because the merry-go-round is turning while the ball is in the air...
By the time the ball gets there, my friend has moved.
Exactly. From your perspective on the spinning platform, it looks like the ball mysteriously curved way off to the side.
But the ball actually flew straight. It was me and my friend who moved underneath it.
Precisely. The Coriolis effect isn't a real force pushing the ball sideways. It's an apparent force caused by observing motion on a rotating system. The Earth is our giant merry-go-round.
Cool. So how does that apply to wind and water?
There's a simple rule, well, simple to state anyway. Moving fluids, like air and water, get deflected. They curve to the right in the northern hemisphere.
To the right.
And they curve to the left in the southern hemisphere.
Right in the north, left in the south. Got it. So that spin is why the water doesn't just follow the wind.
It's the key. That curve is what turns the water away from the coast, setting up the whole upwelling scenario.
Okay, so we have wind power pushing and Earth's spin curving. Now, you said there's a third driver, something about a 90-degree turn.
Yes. This is where it gets truly mind-bending. When you combine the wind push and the Coriolis curve, you get this amazing, almost unbelievable result. It used to be called Ekman transport, after the scientist who figured it out, but let's just call it the 90-degree turn, because that's what happens.
The water turns 90 degrees away from the wind. How?
Okay, picture this. The wind starts blowing across the water surface. That top thin layer of water starts moving, but boom. Coriolis effect immediately makes it curve 45 degrees to the right of the wind if we're in the northern hemisphere.
Okay, 45 degrees, not 90 yet.
Not yet. But that top layer of water is now moving, and it drags the layer of water just beneath it, like sticky pages in a wet book. But because of friction, that second layer moves a bit slower than the top layer. And because it's moving, Coriolis affects it too, so it curves even further to the right.
So each layer down moves slower and curves more.
Exactly. This continues layer by layer, down to maybe 100 meters or so. Each deeper layer moves slower and is deflected further right. If you could see it from above, this whole twisting column of water would look like a spiral staircase descending into the ocean. That's called the Ekman spiral.
A spiral staircase of water current. Cool. But where does the 90 degrees come in?
Here's the kicker. The spiral is cool, but what matters is the overall movement, the net transport of that entire top 100-meter layer of water. When you average out the direction of all those spiraling layers, the total movement is exactly 90 degrees to the right of the wind direction in the northern hemisphere.
Wait, exactly 90 degrees? That seems too perfect. Like if I push something straight forward, it goes perfectly sideways. How?
It's the physics of friction and rotation on a grand scale. It seems impossible, but that combination of the wind's drag being passed down through layers with each layer being deflected by Coriolis consistently results in this bulk movement at a perfect right angle to the wind. It's amazing, but it's true.
Okay, my mind is a little blown. But this 90-degree turn is crucial.
It is the crucial step for coastal upwelling. Let's use that California example again. The wind blows strongly from north to south, parallel to the coast. Yep. California is in the northern hemisphere, so the net water movement is 90 degrees to the right of the wind.
Okay, wind is south. 90 degrees right would be west, straight out to sea.
Bingo. That constant large-scale pushing of the surface water directly offshore, thanks to the 90-degree turn, creates that massive gap or deficit right along the coast.
And that's the space the cold, deep, nutrient-rich water surges up to fill.
That is the engine. That Ekman transport, that 90-degree turn, driven by wind and spin, is what powers the Great Ocean Elevator along our coasts. Without it, you wouldn't get these predictable, large-scale upwelling zones. Okay, so we've wrestled with the physics, the wind, the spin, the spiral, that crazy 90-degree turn. We know how the elevator gets going. Now for the really exciting part. What happens when that elevator delivers its cargo? The biology.
Yes, the deep sea feast. Let's talk about what makes that deep water so special. You called it a treasure chest. Back to Drip's 500-year wait. What's actually in the treasure chest?
It's essentially plant food. The basic building blocks needed for life to grow in the ocean. Think of them as nutrients.
Like fertilizer for a garden?
Exactly like fertilizer. The main ones are compounds containing nitrogen, like nitrate, phosphorus, like phosphate, and silicon, like silicate. Up in the sunny surface layer, tiny ocean plants are constantly using these up to grow. It's like a busy kitchen that quickly runs out of ingredients.
Because there's so much life growing there.
Right. Then when those plants and the tiny animals that eat them die, they sink. They drift down as that marine snow we mentioned, down, down, down into the deep, dark, cold water.
Where there's no sunlight for new plants to grow and use those nutrients.
Correct. So down there, it's mainly bacteria that get to work. They decompose all that sinking organic matter. This process, called remineralization, basically unlocks those nutrients, releasing them back into the deep water in a dissolved form.
So the nutrients get recycled down deep.
Yes, and because the deep ocean currents move very, very slowly, and there's nothing much using them up down there, these nutrients just accumulate. They build up over hundreds, even thousands of years. The deep ocean becomes this vast, incredibly rich reservoir of fertilizer.
A treasure chest full of plant food waiting for centuries.
Exactly, until the elevator arrives.
Which leads directly to the plankton buffet. When that nutrient-loaded cold water finally reaches the sunny surface, what happens?
Kaboom! It's like adding super fertilizer to a sunlit garden that was starved of nutrients. The only thing limiting growth before was the lack of food. Now food is abundant.
So the tiny plants go wild.
Absolutely wild. These microscopic plants, the phytoplankton, undergo explosive growth. Their populations can double in just a day or two. This sudden, massive increase in phytoplankton is called a bloom.
A phytoplankton bloom. Is this something you can actually see?
Oh, absolutely. These blooms can become so incredibly dense that they literally change the color of the water. It can turn milky, bright green, sometimes even reddish brown, depending on the type of phytoplankton.
Wow.
And these blooms can be enormous, covering hundreds or even thousands of square miles. Scientists can easily see them from space using satellites that measure the amount of chlorophyll, the green pigment in the plants. They show up as these huge, vibrant patches of color.
That is incredible. So a tiny fraction of the ocean becomes hyper-productive.
Hugely hyperproductive. Get this.
Yep.
Upwelling zones. These areas where the elevator runs regularly make up less than 2%, maybe even less than 1% of the total ocean surface area. Just tiny slivers along coasts and the equator.
A really small percentage.
Tiny. But they are so incredibly rich, so packed with life, that scientists estimate they account for somewhere between 20% and maybe even up to 50%, half of the world's total fish catch each year.
Half the world's fish from less than 2% of the ocean. That's unbelievable productivity.
It really highlights how vital these areas are. They are true biological powerhouses, environmental hotspots of the best kind.
And this explosion of plankton at the bottom must set off a chain reaction, right? You called it the feeding chain goes wild.
That's exactly what happens. It's a classic example of what scientists call bottom-up control. The food at the bottom determines everything above it.
So it starts with the phytoplankton, the producers.
Uh-huh.
They make the food using sunlight and those upwelled nutrients.
Check. Then come the primary consumers. These are the tiny animals, mostly zooplankton like krill and copepods, that graze on the phytoplankton. With an unlimited buffet, their populations explode right after the bloom starts. You get these incredibly dense swarms of krill.
Clouds of krill.
Literally, sometimes stretching for miles, and the boom just keeps moving up the food chain.
What's next?
Next up are the crucial forage fish. These are the small schooling fish, think anchovies, sardines, herring, mackerel. They're like the middlemen of the ocean food web.
Why are they so important?
Because they are perfectly designed to eat the tiny zooplankton. They swim through those dense swarms, mouths open, just filtering out food. They efficiently convert that microscopic plankton energy into larger fish bodies. They become the main food source for almost everything bigger.
Like the foundation for the bigger predators.
Exactly. And the sheer numbers are staggering. Remember Drip's journey ending with the sardine? The Peruvian anchoveta fishery, which relies entirely on the Humboldt current upwelling, is often the largest single-species fishery on the entire planet. Millions and millions of tons pulled from the sea, all starting with cold water rising.
Wow. And all those little fish must attract the big guys, right?
Huh.
The higher predators.
Oh, absolutely. The density of forage fish in these upwelling zones is like ringing a dinner bell that can be heard across the ocean. You get huge colonies of seals and sea lions hauling out on nearby shores because food is so easy to find.
Makes sense. Easy commute to the buffet.
Totally. Dolphins, porpoises, sharks, big predatory fish like tuna, they all congregate in these areas to feast. Massive numbers of seabirds, gannets, pelicans, cormorants, puffins form huge nesting colonies nearby.
And the biggest of them all.
Yes, the giants. The massive baleen whales like the blue whale, the largest animal ever to live. Humpback whales, fin whales, they undertake epic migrations, traveling thousands of miles across oceans, often timing their arrival to coincide perfectly with the peak season of upwelling and the resulting krill and fish feasts in places like California, Chile, or South Africa.
So if you want to see whales, go where the upwelling is happening.
You follow the elevator, you're following that incredible chain reaction that started with cold, nutrient-rich water hitting the sunlight, fueling a bloom, feeding the krill, feeding the fish, and ultimately feeding the giants. It all connects back to Drip's journey.
Okay, we know how it works, why it's biologically explosive. Where are the best addresses for this ocean elevator service? Where are these global hotspots?
The most famous and productive ones have a specific name. The Eastern Boundary Upwelling Systems, or EBS for short.
Eastern bounded by eastern.
It means they occur on the eastern side of the major ocean basins, which corresponds to the western coasts of the continents. Think about it. California is on the eastern edge of the Pacific. Peru is on the eastern edge of the South Pacific. Northwest Africa is on the eastern edge of the North Atlantic. And Southwest Africa is on the eastern edge of the South Atlantic.
Ah, got it. Western coasts of continents. And why there specifically?
It's where the combination of large-scale wind patterns and the Coriolis effect, remember right in the north, left in the south, work perfectly with the coastline orientation to drive that 90-degree turn, pushing surface water offshore consistently.
Makes sense. So tell us about these big four EBS hotspots. Which one is the biggest fish producer?
That would be the Humboldt Current System running along the coasts of Peru and Chile in South America.
The one that feeds the anchoveta.
Exactly. It's widely considered the most productive fishery system on Earth, thanks to incredibly strong and persistent upwelling. The winds blowing northwest along the coast, combined with the Coriolis effect turning water left because it's the southern hemisphere, constantly pulls surface water away, allowing that super nutrient-rich water to rise. It's an astonishingly powerful biological engine.
Incredible. What's next? How about the one closer to home for many of our listeners?
That would be the California Current System, stretching all along the west coast of North America, from Baja California and Mexico up past California, Oregon, Washington, even into Canada.
Our local elevator.
Yep. This one is very important, supporting salmon, rockfish, whales, seabirds, but it's also highly seasonal. The upwelling is strongest in the late spring and summer when the northwesterly winds blow consistently. That's when you get the foggy coastlines and the peak biological activity in places like Monterey Bay.
Right, the summer fog, that's a clue. Okay, where else? Africa.
Two major ones in Africa. First, the Canary Current System off the coast of Northwest Africa, Morocco, Mauritania, Senegal.
What's special about that one?
It supports very rich fisheries, crucial for the region. And interestingly, its influence extends to the land. It sits right next to the Sahara Desert. The cold, upwelled water cools the air above it, making the atmosphere very stable and suppressing rainfall. So the ocean upwelling actually helps maintain the dryness of the desert nearby, a direct ocean climate link.
Wow, cool connection. And the other African system?
That's the Benguela Current System, off the southwestern coast, Namibia, and South Africa. This one is often cited as perhaps the most powerful coastal upwelling system in terms of the sheer volume and intensity of the cold water being brought up. It's incredibly productive, famous for its huge populations of Cape fur seals and African penguins.
Those are the big four coastal systems. But you mentioned upwelling doesn't only happen near land. There are different flavors.
That's right. The main type we've discussed is coastal upwelling, driven by winds parallel to the coast plus Coriolis. but you also get equatorial upwelling.
At the equator. How does that work out in the open ocean?
It's pretty clever. Remember the trade winds. They blow consistently towards the west, both just north and just south of the equator.
Okay.
Now, apply the Coriolis rule. North of the equator, the westward wind pushes water, but Coriolis deflects it right towards the North Pole. South of the equator, the westward wind pushes water, but Coriolis deflects it left towards the South Pole.
So the water's being pulled away from the equator line on both sides.
Exactly. It creates a divergence, a splitting apart of the surface water right along the equator. This creates a long, linear gap.
And the deep water wells up to fill that gap.
Precisely. This creates a long, narrow band of cooler, nutrient-rich water stretching right across the Pacific and Atlantic Oceans along the equator, making the open ocean much more productive there than you'd expect.
A highway of life across the ocean.
Yeah.
Cool. Any other types?
There's also what we can call topographically associated upwelling. Bit of a mouthful.
Sounds technical. Does it just mean underwater mountains and valleys matter?
Pretty much. Imagine a deep ocean current flowing along. If it suddenly hits a big underwater obstacle, like a seamount, an underwater mountain, or the steep slope of a continental shelf or an island.
The water has to go somewhere, right? It can't go through it.
Right. So the current is forced upwards. It gets deflected towards the surface by the underwater geography. Submarine canyons are particularly good at this. They can act like channels, funneling deeper, nutrient-rich water up towards the shallower edges, creating localized hotspots of life, like little oases.
Oh, so underwater landscapes can create their own mini elevators. Okay, this is the perfect time for some weird but wonderful facts related to all this. Let's start with my favorite you mentioned, penguins in the desert.
Isn't that wild? You picture penguins on icebergs in Antarctica, right? But you find Humboldt penguins living quite happily on the hot, dry desert coasts of Peru and Chile. And Galapagos penguins live right near the equator.
It seems totally wrong. How can they survive in the heat?
They don't care about the air temperature that much. They care about the water temperature and the food. The powerful Humboldt current upwelling brings frigid Antarctic origin water right up to the coast, packed with the anchovies and squid they love to eat.
So they're living in a desert landscape, but swimming in chilly, food-filled water.
Exactly. Their entire existence there is a testament to the power of upwelling to create a rich marine environment, even next to a barren landscape. They followed the seafood buffet, not the warm weather.
Amazing. Okay, weird fact number 2, glowing tides, bioluminescence.
Yeah, this is beautiful. Sometimes the nutrient boost from upwelling causes enormous blooms of specific types of phytoplankton called dinoflagellates.
Dinos, like dinosaurs.
No, dinoflagellates. Many of these have a cool defense mechanism. When they get disturbed by a wave crashing, a fish swimming by, even your hand moving through the water, they emit a flash of bright blue light.
Bioluminescence. Cool.
Really cool. So when upwelling causes these specific dinos to bloom in the billions and billions,
And the whole ocean starts glowing at night.
when the waves break or boats move through or fish swim, it triggers this mass flashing, creating these spectacular, eerie, electric blue light shows along the coast. It looks like pure magic, but it's just biology fueled by upwelling nutrients.
I would love to see that. Okay, last weird fact, and this connects to something we mentioned earlier, the fog secret. Why is it so foggy in places like San Francisco or coastal Peru in the summer?
It comes directly back to that cold, upwelled water. That elevator brings water that might be only 11 or 14 degrees Celsius, that's 52 to 58 Fahrenheit, right to the surface, often just offshore.
Brr. That's really cold for surface water, especially in summer.
It is. Now imagine the typical air moving in from the wider ocean. It's often warmer and carrying a lot of moisture, water vapor.
Okay, warm, moist air hits the cold water strip.
What happens when warm, moist air hits a cold surface? Like breathing on a cold window.
It fogs up. Condensation.
Exactly. The cold water chills the air right above it so much that the air can't hold its moisture anymore. The water vapor instantly condenses into trillions upon trillions of tiny liquid water droplets. We see those droplets as fog.
So that thick, chilly coastal fog is literally the physical evidence that the upwelling elevator is running and bringing frigid water to the surface.
That's precisely it. The fog bank is like a sign saying upwelling in progress. It's a direct link between deep ocean physics and the weather you feel on land. So these upwelling zones are clearly incredible engines of productivity. They're powerhouses. But that very intensity, that reliance on specific conditions also makes them really vulnerable.
Vulnerable to what?
To both natural changes and, increasingly, to human pressures.
Yeah.
Let's start with a big natural cycle, El Nino. You could call it nature's pause button for upwelling, especially in the Pacific.
El Nino. We hear about that in the news. How does it affect the elevator?
Okay, remember the normal situation off Peru. Strong trade winds blow west, pushing warm surface water west, allowing the cold water to upwell strongly in the east.
Got it. That's the normal unstate.
Right. During an El Nino event, those trade winds weaken dramatically. Sometimes they even reverse and blow eastward for a while.
Winds slack off.
And when that happens, that huge pile of warm surface water that was pushed up against Australia and Indonesia, it sloshes back east across the Pacific like water sloshing in a giant bathtub.
Warm water floods back towards South America.
Exactly. This creates a much thicker, much deeper layer of warm water sitting right on top of the normally cold upwelling zone off Peru and Ecuador.
And you called that warm water a cap.
It acts exactly like a sturdy lid or cap on the ocean. That deep, cold, nutrient-rich water simply cannot push its way up through that thick, warm layer. The elevator gets stuck. Upwelling basically shuts down or becomes very, very weak for months.
The elevator stops, so the nutrient delivery stops.
Correct. The fertilizer supply gets cut off.
And the consequences.
Immediate and devastating for the ecosystem. The phytoplankton bloom collapses because there are no nutrients. The intravetta that rely on the plankton either starve or migrate away to find food. And then the seabirds, the seals, the sea lions that depend on the intravetta suffer massive die-offs from starvation.
Wow. So El Nino just pauses the whole system and everything crashes.
It's a stark reminder of how finely tuned and dependent these ecosystems are on that continuous upward supply. It shows the system's sensitivity.
Okay, that's a natural disruption. What about longer-term changes, like climate change? You mentioned a climate tug-of-war.
Yeah, this is a really big area of research right now, and it's complicated. There are two main competing pressures from climate change acting on upwelling.
A tug-of-war. What are the two sides pulling?
Okay, pressure number one, stronger winds. Some evidence suggests that as the planet warms, land masses heat up faster than the oceans. This bigger temperature difference between land and sea could strengthen the winds that blow along the coasts, the very winds that drive upwelling.
Stronger winds. That sounds like it would mean more upwelling, right? A stronger push.
Logically, yes. More wind stress should mean more Ekman transport, more water pushed offshore, and therefore stronger upwelling. That's one side of the rope.
Okay, what's pulling the other way?
Pressure number two, a sturdier cap. As the ocean surface warms overall due to global warming, the temperature difference between the warm top layer and the cold, deep water gets bigger.
Right, the surface gets warmer, but the deep stays cold.
Exactly, and a bigger temperature difference means a bigger density difference. That warm surface layer becomes even lighter, even more buoyant compared to the cold water below. This makes the ocean more layered, more stratified. It creates a stronger, more stable lid on top.
So the cap gets harder to punch through.
Precisely. Even if the winds get stronger, they might have a much harder time pushing that extra warm, extra light surface layer away and allowing the deep water to break through that stronger stratification.
So it's a battle. Stronger winds trying to increase upwelling versus a stronger cap trying to suppress it. Who's winning?
That's the multi-billion-dollar question scientists are racing to answer. The models and observations are complex. It might vary by region. Some areas might see stronger upwelling, others weaker. The most likely outcome seems to be that these systems will become more volatile, more unpredictable, maybe periods of intense upwelling, followed by sudden shutdowns. The future is really uncertain.
More unpredictable. That sounds stressful for the ecosystem.
Extremely. And it's not just the amount of upwelling that might change, it's the quality of the water being upwelled. This brings in chemical stressors.
Chemical stressors, what do you mean?
Remember drip waiting in the deep for 500 years? While down there, natural decomposition of marine snow uses up oxygen. So that deep water is already naturally low in oxygen. Scientists call it hypoxic.
Okay, low on air.
And that same decomposition releases carbon dioxide, making the deep water naturally a bit more acidic than the surface water.
So it starts off low oxygen and slightly acidic.
Yes. But now the entire global ocean is absorbing massive amounts of extra carbon dioxide from the atmosphere from us burning fossil fuels. This is causing ocean acidification everywhere.
Right.
So that deep water, before it even gets upwelled, is becoming even more acidic and even lower in oxygen than it used to be naturally.
Uh-oh. So future upwelling might bring up water that's kind of corrosive.
That's exactly the concern. Water that's both low in oxygen and more acidic is really stressful, even lethal, for many marine organisms, especially creatures that build shells or skeletons out of calcium carbonate, things like crabs, oysters, mussels, corals, and crucially tiny swimming snails called pteropods.
Pteropods. Never heard of them.
They're incredibly important. They're like potato chips for many fish, especially young salmon. If increasingly acidic water makes it hard for them to build their shells, that could have huge ripple effects up the food web.
Wow. So the elevator might deliver water that's less helpful or even harmful.
That's a major worry. And finally, on top of all these natural and climate-related changes, we have the direct human pressure. Overfishing and feeding chain disasters.
Right, because these areas are so full of fish, they attract a lot of fishing.
Exactly, they're prime fishing grounds. But their productivity, while immense, isn't infinite. If fishing fleets catch fish faster than the fish populations can reproduce, that's overfishing. It can lead to the collapse of fish stocks, like what happened historically with the Peruvian anchoveta and other fisheries around the world.
And taking too many fish out doesn't just affect that one species, does it? You mentioned a feeding chain disaster.
Right. It causes what scientists call a trophic cascade. Trophic means feeding level. If you remove too many of one key player, it throws the whole system out of whack.
Can you give an example?
Sure. Imagine you overfish the large predatory fish, like tuna or large cod, in an upwelling zone. What happens to the fish they normally eat? The medium-sized fish.
Their numbers would probably explode with fewer predators around.
Exactly, but then that huge population of medium fish might start eating way more of the smaller zooplankton than usual. They could graze down the zooplankton population.
And if the zooplankton disappear?
Then the link between the phytoplankton bloom and the rest of the food web is broken. Even if the upwelling is strong and the phytoplankton are blooming, the energy can't move up the chain effectively. You can end up crashing the whole system from the middle out or the top down.
So it's a really complex balancing act. Climate change, water chemistry, and fishing pressure all interacting.
It's incredibly complex, and these vital ecosystems are caught right in the middle.
Wow, what an incredible journey we've been on, following Drip the Droplet and uncovering this hidden ocean engine. Let's just quickly wrap our heads around the main points.
Sounds good.
We started with Drip, our 500-year-old water droplet, stuck in the deep, loaded with nutrients.
The treasure chest.
Then we learned about ocean upwelling, this amazing process where strong, steady winds blowing along the coast, combined with the Earth's magic spin, the Coriolis effect,
Causes that surprising 90-degree turn of surface water, pushing it offshore.
which creates the space for the great ocean elevator to kick in, bringing that cold, nutrient-rich deep water surging up to the sunlit surface.
Fueling the plankton buffet. Those massive phytoplankton blooms that turn the water green and form the base of the entire food web.
A food web that explodes with life, supporting huge swarms of krill, vast schools of forage fish like sardines and anchovies.
Which in turn feed millions of seabirds, seals, dolphins, tuna, and even the largest whales on Earth. These small upwelling zones account for maybe half the world's fish catch.
We learned about the big four hotspots, the Humboldt, California, Canary, and Benguela currents, and other types like equatorial upwelling, and the cool side effects, like penguins in deserts, glowing tides, and coastal fog.
Don't forget the fog, direct evidence of the elevator running.
Definitely won't forget the fog now. But we also touched on the serious challenges. These systems are sensitive.
Very sensitive. Natural cycles like El Nino can hit the pause button, causing ecosystems to collapse temporarily.
And looming large is climate change. That tug of war between potentially stronger winds and a potentially stronger, warmer cap on the surface, making the future uncertain.
Plus the added stress of the upwelled water itself becoming more acidic and lower in oxygen.
And the constant pressure of fishing, needing careful management to avoid overfishing, and those damaging feeding chain disasters.
Yeah, these zones are powerhouses, but fragile ones in many ways. They connect the deep sea to the surface, the ocean to the atmosphere, and ultimately they are critically important for us, for food, and for the health of the whole planet.
It really changes how you think about the coast. That chilly summer fog isn't just weather. It's a sign of this incredible deep ocean process feeding maybe humpback whales offshore. It's all connected.
It absolutely is. So maybe the next time you feel that cold coastal breeze or see fog rolling in or even hear about El Nino on the news, you can think about Drip's journey.
Think about that invisible elevator.
Exactly. And maybe ask yourself, this giant ocean engine is so vital, but it's clearly under pressure. How stable is it really? And what can we all do? How can we live to help protect this incredible life-giving upward whoosh of the ocean?
A really important thought to leave us with. Thank you so much for sharing all this today. It's been fascinating.
My pleasure. It's an amazing story to tell.
We really hope you enjoyed this incredible story today. Join us next time for another adventure on Saltwater Stories.